All right, I'm going to spend a little bit of time here trying to go through some of the problems from moment of inertia and torque practice. And I'll try to do this so that hopefully you can follow along and see what I'm doing. I'll start at the top of this page and see if I can work through some of these problems. The first one, determine the moment of inertia for two masses, one 2 kilogram, the other 4 kilogram, connected by a 3.2 meter massless rod being rotated around the center of the rod. So the thing to understand about moment of inertia is that moment of inertia describes not just the inertia of the object, meaning how difficult it is to get that object to move or how difficult it is to get it to stop moving, but it's describing instead how difficult it is to get an object to rotate or how difficult it is to get the object to stop rotating. Part of some of the activities I gave you early on was looking at how easy it is to balance something on a stick. And a good example of this is tightrope walkers. If you ever see a tightrope walker, they're holding a stick. They walk with a big pole in their hands. They don't walk with a short stick. They walk with a pole that's maybe 10, 15 feet across. Why is that? Because having that mass extended farther away from the center makes it less likely that that rod will rotate. And if you're walking as you're trying to balance on a piece of rope, if you have a stick that's 15 feet long in your hands, that stick isn't going to rotate very easily. It gives you plenty of time to adjust and balance out your walking so that you don't fall. If you tried to do the same trick and you had a little stick, maybe a broomstick, you start to lean over, you can't adjust. There's no way to adjust, you're going to fall off. Think about if you are walking somewhere and trying to balance. I used to have a pole in the backyard of the house I grew up with to keep us from backing off the driveway. It was just a big metal pipe that ran like this and then curved and attached in the ground. And I would walk across this pipe and try to balance. First thing I would do is throw my arms out to my sides to try to balance. Why? Because having my mass extended farther away from the center of rotation makes it less likely I'll fall. If you're ever trying to balance and walk on a thin line or a very small thing, hold your arms close to your body. See how well you can balance. You're probably going to fall over, so maybe don't do that. Your first instinct is to throw your arms out to the side to catch your balance. So, determining moment of inertia, the inertia of an object that could rotate. To determine the moment of inertia, the basic formula for that is I mass equals mr squared. I'm going to see if I can get this to focus in a little bit better. I mass, the moment of inertia I, of a mass is equal to the mass times the radius squared. So easy enough to determine moment of inertia for two masses, one 2 kilograms, the other 4 kilograms, connected by a 3.2 meter massless rod being rotated at the center of the rod. Okay, so let's figure out what this is talking about. Two masses. One is 2 kilograms, the other mass is 4 kilograms, connected by a 3.2 meter massless rod. And I apologize, that's not focusing very well. Hold on, I'm going to try to do the same thing here with a pen if I can. All right, well, I don't have a pen close enough by, so we'll see what I can do as is. All right, so if the formula for any mass is I mass mr squared, this is rotating at the center, so we need to know that this is the center and it's the axis of rotation. If this is the center, the whole thing is 3.2 meters. That tells us that this side and this side are half of this, 1.6 meters, 1.6 meters. So mr squared for the 2 kilogram mass, I for 2 equals mass, 2 kilograms, times radius, 1.6 meters squared. For this mass, the 4 kilogram mass, I4 is equal to 4 kilograms times 1.6 meters squared. What's the moment of inertia of the rod? Well, okay, so this is the formula for a mass. These formulas you don't have to memorize. If you know mr squared, that's good. You should have that memorized. But you don't have to memorize all of these variations, because what these variations represent is the fact that not every object has its mass evenly distributed around its center of rotation. A mass, this counts for like a point mass, a single point in space that has some mass. So that we can treat as a single object. So we just treat the mass as itself. But when you have a disk, what you see is that some of the mass of the disk is out at the edges. Some of the mass of the disk is at the center. Some of it is in between that. So what happens is effectively, you're only looking at half of the mass times the radius squared, because some of the mass is at the center. And if it's at the center, it's not rotating. Wait, what does that mean? That means if I have something spinning around, the mass at the center, the very, very center, isn't moving. It's just kind of rotating in place. But it's not, it's doing this. It's spinning in place. It's not doing this. It's doing this. So the very center of this pencil is kind of not really moving much. It's not very difficult to get it to do that. So we use for a rod this formula, I rod from the center, if it's rotating at the center, like this one is, 1/12 mass times length squared. That means about 1/12 of its mass is out at the extreme end, and the rest of it is closer to the center. Okay, I rod end, what does that mean? That means instead of a rod that's rotating like this, the rod is rotating at its end, which is actually much more difficult to make happen. So this is only 1/3 ml squared. It's a fraction here that is much larger, indicating that the moment of inertia for this one is much larger. So I rod end, I rod center. We've also got one for a disc, we've got one for a hoop. There are more. Again, you don't have to memorize those. Those will be given to you on the AP exam if they come up. So let's figure out the mass, or sorry, the I, moment of inertia for the rod. The formula for I rod center is 1/12 mass of the rod. This is a massless rod. Okay, so 0 kilograms times, it's rotating at its center, times the length squared. The length. So that's the full length of the rod. Notice for a rod, we don't use R, we don't use radius from axis of rotation, we use L for length of the rod. So in this case, we will put the full 3.2 meter value in there squared, but guess what? It doesn't matter. 0 times 1/12 is 0, 0 times 3.2 squared, 0. So all of this adds up to 0 moment of inertia. What's our unit for a moment of inertia? If it's mass times length squared, our unit for I will always be kilograms times meters squared. So I'm going to do some of the math here real quick. See if we can't come up with a good answer for this. 2 times 1.6, here I'll pull you into my calculator land. 1.6 times 1.6 equals 2.56 times 2 equals 5.12 kilograms times meters squared. And then 4 times 1.6 squared, 1.6 times 1.6 times 4 equals 10.24 kilograms meters squared, plus 0. So 5.12 plus 10.24 gives us 15.36. Let's look at our answer. Oh, hey, look, our answer is 15.36. So the total moment of inertia for that system is 15.36. Now, if we were being real here, we have 2 sig figs on either of these, which is kind of a bad way to design this problem. The rounded off answer should be 20 kilograms times meters per meter squared. Yikes, that's ugly. Okay, so what I probably should do is I should go back into this. I should make this 2.0. I should make this 4.0. And then our answer should instead be 15 kilograms times meter squared. All right, next problem. In problem 1, determine the moment of inertia for the system if it is rotated on the end with the 2 kilogram mass. Okay, so now let's look at, instead of all of this, let's look for number 2. This is number 1, this is number 2. It's rotated on the end with the 2 kilogram mass. So same picture up here. 2 kilograms, 4 kilograms, 3.2 meters, and it's rotated here, which means this is now rotating around like this. This whole part is going around. This is moving around like that. So this stays stationary, this moves around. Hey, wait a minute, hold on. There is our clue to how this changes the problem. If this part is stationary, now this is going to have mass times radius squared. There is no radius, it's stationary. It's at the center of the axis of rotation. So mr squared for this is 0. This doesn't provide any moment of inertia to the system because it's not moving. This one does. So now we've got a mass. I of the 4 kilogram mass is equal to mass times radius squared. This rod is still massless, so we don't have to worry about it. Let's look at this. The mass of this is 4 kilograms. The radius of this now, because this is the axis of rotation, the radius that this is moving at is 3.2 meters squared. So let's plug in the numbers because we've done all the physics we need to do. 3.2 times 3.2 equals 10.24 times 4 equals 40.96. Hey, look at that, 40.96 kilograms times meters squared. Tearing it up. Number 3. From problem number 1, determine the moment of inertia if the rod, if it has a mass of 6 kilograms. Moment of inertia of the rod if it has a mass of 6 kilograms. So we're going back to this drawing, only now we're saying that the rod has a mass of 6 kilograms. Well, it's a rod rotating at its center. So I rod center is equal to 1/12 mass times length squared equals 1/12 times the mass of the rod, which is now given in the problem as 6 kilograms, times length of the rod, which is 3.2 meters, squared. All right, so this should be easy enough. 3.2 times 3.2, 10.24 just for this part, times 6, divided by 12, 5.12. So the answer here is 5.12 kilograms times meter squared. Ah, cool, perfect. All right, number 4. Use the information from problems 1 and 3. Whoops, sorry about that, y'all. I got to shift up here so you can see what I was doing. My focus is fantastic. All right, so I rod center, 1/12 mass times length squared, 1/12 of 6 kilograms times 3.2 meters squared gives us 5.12 kilograms meters squared. All right, so now we can go to question 4. Use the information from problems 1 and 3 and determine the moment of inertia for the system. 1 and 3 determine the moment of inertia of the system. So 1 was the moment of inertia for the 2 masses and a massless rod, which was 15.36. All right, so we've got that number in our heads. We know that number 1 is going to be equal to 15.36 kilograms times meters squared. All right, let's go down here and see what all we're dealing with. The problem for number 4 is saying 1 and 3, and we said that 1 is 15.36 kilograms times meters squared. And problem 3, for problem 3, it was the moment of inertia of the rod if it had mass. So what we're saying is now problem 1, the mass of the rod is there. So we go back to 3. 3 was 5.12 kilograms times meters squared. We can just add those two things together. That gives us 20.48 kilograms times meters squared. All right, no problem there. Moving along. Number 5, determine the moment of inertia for a 4 kilogram, 2 meter long rod rotated around the end of the rod. All right, so let's take a look at this one. I rod end up here is 1/3 ml squared. So our formula for number 5 is 1/3 ml squared. Number 5 says 4 kilogram, 2 meter long rod. I equals 1/3. That was a 4 kilogram, 2 meter long rod. 2 squared is 4, times 4 is 16. 16 divided by 3, 5.33. That gives us our answer of 5.33 kilograms times meter squared. Number 6. Number 6 says, what is the moment of inertia for a rotating disc that has a mass of 6 kilograms and a radius of 2 meters? Rotating disc. Oh, okay, cool. So we will go up to our formula sheet for I disc, 1/2 mr squared. I equals 1/2 mr squared. We are told in this problem that it is a mass of 6 kilograms. And our value for this is a radius of 2 meters squared. 2 times 2 is 4. So 2 squared is 4. Times 6 is 24. Half of that is equal to 12 kilograms times meter squared. Number 7. Number 7 says, if a 1.5 clay blob is placed on the outer edge of the disc in the previous problem, what is the rotational inertia of the system? So the only thing that's changing is we're adding a 1.5 kilogram clay blob at the outer edge of the disk. So up here, this one is a disk. This one is a disk with a blob of clay stuck on the side of it. The only thing that's changing is the blob of clay. Clay can be treated as a mass, I equals mr squared. So let's figure out just the value for the blob of clay. For the blob of clay, it is, m is, let's see, 1.5 kilograms. And we know that it's on the same disk as the previous problem, which had a radius of 2 meters. 2 meters squared. 2 times 2 equals 4, times 1.5 equals 6. So the blob of clay has 6 kilograms times meters squared moment of inertia. The previous problem was 12. 12 plus 6 equals 18 kilograms times meters squared. All right. So we're just solving for the new component and adding it into the total. Number 8. Number 8 says the torque of a 32.0 Newton meters. Okay, so torque is a force applied at a distance, newtons times meters, on a certain wheel causes an angular acceleration of 25 radians per second squared. What is the wheel's moment of inertia? Okay, so this is a torque problem. So let's go up to our formulas and let's see what we can use out of our torque formulas. Torque, remember, is the funny little tau, right? So it's the Greek letter tau. That can be a force applied at a radius, or we have this formula. Torque is moment of inertia times angular acceleration. That one looks familiar. Torque is moment of inertia times angular acceleration. So let's write both of those down. So for problem 8, torque, well, if I could draw a tau, that would be great. Torque is equal to a force perpendicular to a radius. Torque is also equal to moment of inertia times angular acceleration. All right, so problem 8 tells us, let's go back and look at the problem here. It says a torque of 32 Newton meters on a certain wheel causes an angular acceleration of 25 radians per second squared. What is the wheel's moment of inertia? So we're trying to find I. This has I in it, so we're going to use this formula. It has A and it has torque. Let's solve this formula for I. So I is equal to the torque divided by angular acceleration. Hopefully you see that this looks a lot like our force equation, Newton's second law. Force, that's like a torque. Torque is a rotational force, is equivalent to moment of inertia. Inertia is mass for linear objects times angular acceleration in translational or linear situations. That's just A. F equals ma. So this is saying mass is equal to a force divided by its acceleration. We're not dealing with a linear quantity, so we don't use that. We use the rotational quantities instead, but the analog is there. So I will be equal to torque, 32 newtons times meters, divided by angular acceleration, 25 radians per second squared. Now we can say 32 divided by 25 equals 1.28 kilograms times meters squared, which should be the answer. Number 8. Hey, look, 1.28 kilograms times meters squared. All right, clearly I'm running out of paper here. Let's flip over to the other side. Let's see if I can keep going. Number 9, the world's heaviest hinged door. This is something that I'm sad I don't get to share with you guys in class. So we'll take a look at it and see what it looks like. Oh, okay, here it is. The world's heaviest door is found at Lawrence Livermore Laboratory. This is a picture of it. Hopefully you can see that. This is a lady in some fashionable bell bottoms pushing this door open. This door is designed so this huge hinge and this massive door can be pushed open by one person. You can see the groove that it's digging into the concrete, or maybe it's set into the concrete for it to rotate out. Look how thick that door is. That's going into a building that has a thickness approximate to that as well. So why do we have this door? What the heck? What's this door for? Let's see. Oh, goodness. The world's heaviest door. Maybe it's because it's a hinged door. This has a new door. All right, well, let's forget that. Let's go back to this. This door was made in the 70s, I think. It's at Lawrence Livermore National Laboratory because this door was built on, I believe it was a, let's see, here we go. You can find the website describing this. It is a 97,000-pound concrete-filled door used to shield the rotating target neutron source. So a particle accelerator of some sort, a lot of radiation, and they didn't want that escaping, so they made this huge concrete building with a door that's 8 feet thick, 12 feet wide. Kind of crazy. They can open it with a remote control, but a single person could actually push it open. All right. Now I want to go back and find out about this this door in Japan. I know this is what you guys really care about. This is more important than the physics. Radiation door. 1.44 million pounds. All right, so maybe this door doesn't rotate on a hinge. There's no picture of the door. I don't see a picture of the door. Horrible. This is the place that it's at, but I don't actually see the door. All right, so forget it. We just don't care. Don't care, letting it go. Going back to the question. Question is, this hinged door, 44,000 kilograms, has a moment of inertia of 87,000 kilograms times meters squared, and a face width of 2.4 meters. So it's 2.4 meters across. Neglecting friction, what steady force applied to its outer edge and perpendicular to the plane of the door can move it from rest through an angle of 90 degrees in 30 seconds. Whew, that's a lot of information. Let's see if we can tackle this problem. So number 9, we know that it has a mass, 44,000 kilograms, has an I value of 87,000 kilograms times meter squared, and it has a face width. What number, or what is that useful for? Well, the door rotates on an axis of rotation like this. Here's the axis of rotation. Here's the door moving, opening, and closing. The radius of that axis of rotation is the face width. So our value is 2.4 meters. Neglecting friction, what steady force applied at its outer edge, perpendicular, so force is what we want to know. A perpendicular force, what is that force? Applied at the outer edge, perpendicular to the plane of door, can move it from rest through an angle of 90 degrees in 30 seconds. So rest, this is a rotating object. If it's at rest, that means its angular velocity initial is 0 radians per second, and it's moving from rest through an angle of 90 degrees in 30 seconds. Time equals 30 seconds, angle of 90 degrees. So we have to know what that 90 degrees represents. So I'm switching out to a pen here. Sorry, it's getting hard to see. Probably was hard to see before. So this is telling us that the angle, and remember angle is theta. Theta is 90 degrees. And we need to convert that to radians. So how do we do that? We want to convert theta equals 90 degrees. We want to convert that to radians. So we want to get rid of degrees. So let's get rid of degrees. 1 time around a circle is how many degrees? 360 degrees. How many radians is that? 2 pi radians. 2 pi radians is equal to 360 degrees. If this and this are equivalent, then this divided by this is 1. If you multiply anything by 1, you don't change it. So that means we can take 90 degrees, multiply it by 2, divide by 360. Times 2, got to go scientific for this, times pi, where is my pi on here? There we go. Equals 565 divided by 360 degrees equals 1.57. We have infinite sig figs here. This is infinite because that is part of your formula. 360 is 3, 90 is 2. So we'll call this 1.6 radians. 1.6 radians. All right, so we've got some information. And the question is, what is the force applied to this door that can make it move from rest through an angle of 90 degrees in 30 seconds? All right, so we've got a distance, we've got an initial velocity, we've got a time. That means we're going to have to do some more work here. Let's stop and figure out what we can do for this problem. We want force. Clearly, this is an object that's rotating, so it's got torque forces acting on it. We know from that previous problem that we just did that torque is equal to a force perpendicular to a radius perpendicular. Torque is also equal to I times alpha, moment of inertia, times angular acceleration. We want to find this. So this is what we need. We've got a radius, 2.4 meters. Let's go ahead and set this problem up, divide both sides by r perpendicular. That gets rid of that. So what we are looking for to find this force, this is no longer looking at torque. This force is now equal to moment of inertia times alpha divided by r perpendicular. Moment of inertia we were given for the door, 87,000 kilograms times meters squared, times alpha, we don't have alpha, divided by r squared, or sorry, r perpendicular, 2.4 meters. We need to know what alpha is. Alpha is acceleration. Can we find acceleration? Well, if we were doing a linear problem, let's come over here to the side. Acceleration is equal to a change in velocity over time. Acceleration is equal to velocity final minus velocity initial over time. Let's convert that to rotational quantities. Alpha is equal to final velocity, angular velocity, minus initial velocity divided by time. Time doesn't have a rotational quantity. Can we solve for this? Heck yeah, we can. Let's go over here. Angular acceleration is equal to final angular velocity. Let's see. We don't have final angular velocity. We have time, 30 seconds. What can we need? Oops, sorry. So what we have to do is approach this as a kinematics problem. So for kinematics, we are looking at something that's rotational. You can have an initial velocity, you can have final velocity, you can have change in angle, you can have angular acceleration, and you can have time. Just like we would do any of our kinematics problems, we can approach this with the same math. Omega naught, 0 radians per second. Final velocity, we don't know. Delta theta, 1.6 radians. Angular acceleration, we don't know. Time is 30 seconds. We now have enough information to solve for alpha. So ignore my approach of trying to solve it like this. What was I thinking? We'll go here instead. This is a safer road to tread. So we need a kinematics formula that's going to get us there. And to find a kinematics formula that will get us there, we need to think about our kinematics problems, our kinematics formulas. Let me pull out my formula sheet. And I took a quick pause there to pull up the formulas so you didn't have to watch me do that. So here is my kinematics formulas. I just pulled these up on Khan Academy because I don't have a formula sheet handy. We've got V equals V naught plus AT, delta X equals V plus V naught divided by 2 times T, delta X equals V naught T plus 1/2 AT squared. There's also that X naught that should be added in there. And then velocity squared equals initial velocity squared plus 2 times acceleration times delta X. So what are we looking for to solve this problem? All right, so we need to think about what is given to us in the problem. We have initial velocity, we have delta theta, and these things are analogous to initial velocity, delta X, and T. So we have V naught, delta X, and T. So let's find a formula that has V naught, it has delta X, this doesn't have delta X, so we can eliminate the first one. This one has V naught, this one has delta X, it has T, but it doesn't have A. We need acceleration. This has V final, which we don't have, so that's no good. The third one, delta X, V naught, T, 1/2 A, T squared. Hey, this looks like our best bet. This one here at the bottom isn't going to work because it has velocity final, which we also don't have. So let's go for kinematics formula 3. So kinematics formula 3 is delta X equals V naught T plus 1/2 alpha, A, T squared. Now I'm going to go back to our problem, and I've written over here delta X is V naught T plus 1/2 AT squared. I'm going to convert these to rotational formulas, to a rotational formula. Delta X is analogous to delta theta, is equal to V naught, which is omega naught, times T plus 1/2 times alpha T squared. We have this given to us, we have this given to us, this given to us, this given to us. The only thing missing out of this is alpha, which we need alpha to solve this problem. So let's rearrange this guy to solve for alpha. Can we simplify it real quick? Omega naught is 0 radians per second, 0 times T. I'm going to drop out of the problem. So simplifying it, we get 1.6 radians is equal to 1/2 alpha times T squared, 30 seconds squared. Okay, now that looks like a much easier problem. Let's see if we can calculate this guy out and solve this an alpha. 30 times 30 is 900 divided by 2 450. So 1.6 radians is equal to 450 alpha seconds squared. That's just a unit. Let's divide both sides by 450 seconds squared. And that will give us over here 1.6 divided by 450. That cancels all this mess out. Alpha is equal to 1.6 divided by 450 equals, going back up here at the top, not doing this, alpha is equal to 0.003536 radians per second squared is our alpha value. 0.0036 radians per second squared. Let's put that into our formula. That times 87,000 divided by 2.4 equals 128. Wow, okay. So our force required to open this door from this moment of inertia times angular acceleration divided by the radius of the door is equal to 128. Let's see what the answer is. Oh, look at this. Let's see what we got. 126.5 newtons. Okay, you know what? I'm going to call that close enough, right? So it's a rounding error. We had 2 sig figs. This would round to 130 newtons. This would round to 130 newtons. So I think we're good in either case. So number 9. All right, I'm going to call it there for now. And that's probably as much video as you guys can bear for a while. And I will share this and everybody can go through these problems on your own. Thanks. Have a great day.